So we're in section 9.8. And last time we talked about Taylor polynomials and Maclaurin polynomials, which were polynomial approximations to functions. And generally, when we do a polynomial approximation, the higher the degree of the polynomial, so the more terms that we take, the more accurate our approximation. We can many functions, a lot of functions, we can represent exactly with an infinite series that we call a power series. So that's what we're going to work with today. Is rather than just a limited number, finite number of terms of a polynomial, we're going to turn that polynomial into an infinite series. So we're going to define what we mean by a power series. So a power series has the form sum from 0 to infinity of a sub n x to the n. And I'll just write out a few terms. And we just continue summing these terms. And x is a variable. And if we center our power series about some constant, we have the sum n equals 0 to infinity of a sub n x minus c to the n power. Plus, and we just keep summing. So what we're doing with power series is we look at these power series as a function of x. Since x is a variable, they're a function of x. And we say that the domain of a power series, the domain of these, is the set of x values for which these converge. So we're tying our power series back to our work with convergence, because we want to see if we're representing some function as a power series, we want to know when that power series is going to converge. So we have to figure that out, and that's the domain of our function. So we have a few cases that happen with power series. So for convergence, we can have exactly one of three cases. So exactly one of these is going to be true. And this is where we're considering a power series centered at C. So our first case is that the power series will converge only at C. So that would be a power series that would not be particularly useful. It would only converge at that one particular value. Our second case, second possibility, is it will converge absolutely for when the absolute value of x minus c is less than some r. And it will diverge for x minus c greater than this particular r. And r is just a real number greater than 0. So we'll have in this case we'll have a range of x values for which our series converges. And our third condition, it's when our power series are very useful, is that it converges for all x. So exactly one of these is going to be true about a power series representation of a function. So it's going to converge at one particular value, the value that we expand our power series about. It's going to converge for some range of values and diverge for all other values, or it's going to converge for all x. And depending on how we use the power series, is our usefulness and our application is going to depend on what values of x this power series converges for. We call r the radius of convergence. And if condition 1 is true, if it converges only at c, we say the radius of convergence is 0. We just have the 1 point. And if it converges for all x, we say the radius of convergence is infinite. The set of values, this second condition gives us an interval in which our power series converges. So that set is called the interval of convergence. So we have a radius of convergence. It tells us how far around our C, our center point, our point that we expanded about, how far around that we have convergence, and we call the set of x values the interval of convergence.
Is that only for the third condition or for the second?
Well, so for the third condition, we'd say the interval of convergence is infinite, right? So a couple of important things to remember when we determine convergence. The endpoints of our interval, our series converges or diverges at the endpoints independently of what the power series does inside the interval of convergence. So when we test for convergence, we have to test the endpoints of our interval separately. So I'm just going to say here that the endpoints, our series converges at the endpoints independently of the points inside the interval of convergence. So what this is telling us is we have to test the endpoints separately when we're testing a power series for convergence. We have to test the endpoints separately, and that's an easy one. That's an easy one to forget. So we determine our interval of convergence, our radius of convergence, our interval of convergence, and then we need to test the endpoints. And that will give us a picture of when our power series converges or diverges. For power series, we usually use the ratio test, which is nice. We can determine the interval of convergence, find the interval of convergence, usually using the ratio test. The endpoints, to determine the convergence or divergence of the endpoints, often then we have to use separate tests. Some of our other tests to test the endpoints for convergence. So, any questions on convergence of power series? So let's look at a couple of examples. We're going to go back to the series that we looked at on Tuesday. We did a Taylor series expansion, a Taylor polynomial expansion for f of x equals 1 over x. And we have that centered, we expanded about x equals 2. And we used a couple of expansions to approximate 1 over 2.8. When we found the first 4 Taylor polynomials, we said that p of 4 of x, this is what we found the other day, was 1/2 minus 1/4 x minus 2 plus 1/8 x minus 2 squared minus 1/16 x minus 2 to the third. So this was our fourth Taylor polynomial that we found for this series. So what we want to do for when we're working with a power series is we want to find an expression for a general expression for the nth term. So we want to be able to write this in sigma notation, with our summation notation. So let's find a general expression. I'm going to rewrite this, p sub 4 of x. I'm going to factor out this 1/2. And I'm going to have 1 minus 1/2 x minus 2 plus 1/4 x minus 2 squared plus 1/8 minus, thank you, minus 1/8 x minus 2 to the third. So I just factored out a 1/2. Can anybody come up with an expression, a general expression for the nth term? What do you think? I'm going to put this 1/2 here. Our signs alternate, right? So we have a -1 to the n. We have our first term positive, so -1 to the n. What's that? So if we start with 0, that would be fine. I kind of like when meds start at 0.
The x minus 2 terms will be like as well.
Right, so let's just put that x, I'm just going to write that over here, x minus 2 to the n, if we're starting at 0, and 1/2 to the n, right? Because 1/2 to the 0 is going to give me the 1, 1/2 to the 1, I get 1/2, and I get the -1 here, and this is the 1/2 that I have out here in front. So everybody agree with that for my nth term? So I could write my Taylor series as a sum, so p of x could be the sum n equals 0 to infinity of, I'll put a 1/2 here in front, 1/2 minus 1 to the n, and I'm going to put this 1/2 inside my parentheses and just say this is x minus 2 over 2 to the n. So that would be a power series representation of this function. So when is now we want to find the convergence or divergence of this series. So what could we could do the ratio test. Anybody see an easier way we could do this? Geometric series. For n, if we start at if we look at this as a geometric series, as long as this ratio, this quantity is less than 1, the absolute value is less than 1, this is going to converge. So let's say that, so this is going to converge when the absolute value of x minus 2 over 2 is less than 1. So this will give us our interval of convergence. So x minus, absolute value of x minus 2 is less than 2, and our interval is 0 less than x less than 4. So that's our interval of convergence. So our radius of convergence, if this is our interval of convergence and we're centered about 2, what's our radius of convergence going to be? Radius of convergence equals 2. And our interval, if we want to find, if we tested our endpoints of our interval are 0 and 4. If we plug in x equals 0 here, I get negative 2 over 2 is negative 1 to the n. So I'm just summing, basically I'm summing negative 1 to the n times negative 1 to the n, which is just 1. So I'm summing 1 from 0 to infinity. So that's going to diverge. And if I plug in 4, I get negative 1 to the n times 1 to the n. So then I just have we're summing minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. So that's going to diverge. So our interval of convergence, our set where our series converges, is going to converge on 0, the set 0, 4. So this power series would represent the function 1 over x for x between 0 and 4. Well, here we said the absolute value of x minus 2 has to be less than 2. If we solve that absolute value inequality, we get this interval, 0 less than x less than 4. So when I go through this, if I solve this inequality, this inequality tells me x minus 2 is less than 2, and negative x minus 2 is greater than 2. So this one gives me that x is less than 4. This one gives me negative x plus 2 is greater than 2. Negative x greater than 0. Switch the things, we get x less than. What? I made a mistake. What's that? Oh, yeah.
I think you can just set at the absolute point when you get rid of the absolute value sign. You can just remove the absolute value sign, but then it's 2.
Right.
And then the second one is x minus 2 is greater than negative 2.
Oh, there we go. That's x minus 2 is greater than negative 2. That's what I wanted. I put my negative sign on that. So there we go. Then we add 2, so x is greater than 0. There we go. So that gives me my interval. That's how we came up with that. All right. Questions on that one? Now, normally what we'll do, we won't necessarily have to come up with a power series, or we'll have a different method of coming up for a power series with a power series than looking at an expansion and trying to figure out a general term. And we'll talk more about that tomorrow. Today we're more interested in figuring out our intervals of convergence. But I like this one because we did this example the other day, and this connects back with the Taylor series. We're going to connect back with the Taylor series a little more tomorrow, putting power series and Taylor series together and figuring out their connection. So let's look at one more example, and then I want to talk about where power series are the most useful is when we talk about derivatives and integrals. So this time we're given a power series, n equals 1 to infinity of x to the n over n times 3 to the n. And we want to find the interval of convergence. So, in general, when we're talking about power series, we will use the ratio test. That's going to be our go-to test for power series. This one would work with the root test. We could use the root test on this one, so we could do it either way. What's that? But this one turns out nice with the root test, doesn't it? Don't you think?
I don't know, but I will never use it.
You'll never use it?
I gotta see the example with the ratio test.
So let's set up the root test, and then we'll do the ratio test. Because I like this because we have these powers of n here. So if we use the root test, we want the limit. We're looking at the limit as n approaches infinity of the nth root of the absolute value of x to the n over n to the n times 3 to the n. And what do we want for our root test? What do we want our limit to be? Less than 1. So we're looking for this. So we're looking at the limit as n approaches infinity, the nth root of x to the n. So we just end up with 1 over the nth root of n. Oh, sorry, and we have an x in the top, and the limit of the nth root. Yeah, we forgot our 3, didn't we? 3 nth root of, so we have 3n. There we go. Maybe we shouldn't have used the root test.
I forgot my ratio test.
Yes, the 3 should be outside. There we go. So we want this to be less than 1. The limit as n approaches infinity of the nth root of n is 1. So we have the limit as n approaches infinity of the absolute value of x over 3 is less than 1. So finally, this is less than 1. This doesn't depend on n. So this is less than 1 when the absolute value of x is less than 3. All right, see? Wasn't that easy? All right, let's look at the ratio test. I just had to remember how to take nth roots, right? So let's look at the ratio test. So let's remember this result. So for the ratio test, we're looking at the limit as n approaches infinity. And our ratio test is we end up with x to the n plus 1 over n plus 1, 3 to the n plus 1 times n 3 to the n over x to the n. And we just need to simplify this. So how does this simplify? How do we simplify this? What do we end up with? X over 3 times the n plus 1, right? X, yes, we have one n.
It doesn't have to
Xn.
go to 1. You can just not,
I'm sorry?
like, can't you just write it as, like, from the n plus 1 as, like, the n goes to infinity goes.
Right. So I wasn't taking the limit yet. I was just simplifying this. Limit as n approaches infinity of xn over 3 to n plus 1. The limit as n approaches infinity of n over n plus 1 is 1. So we just get the limit as n approaches infinity of the absolute value of x over 3. And we want that less than 1. So we end up with the same thing. Absolute value of x is less than 3. So our radius of convergence here is, 3. What's that? Slightly less than 3. So when we're talking about the radius of convergence, we're talking about an open set. So this is of the open set. And so we know our radius of convergence is 3. We need to test the endpoints. So we found it converges inside the interval of convergence. We need to test the endpoints. So we're going to test our endpoints at x equals 3. We're just plugging in x equals 3 into our original expression. We plug in x equals 3 here. We end up with the sum, n equals 1 to infinity of 3 to the n over n 3 to the n. And this is just the harmonic series. So it diverges at x equals 3. At x equals minus 3, we have the sum n equals 1 to infinity of minus 3 to the n over n 3 to the n, which is minus 1 to the n over n, which is the alternating harmonic series, which converges. Because the harmonic series is the alternating harmonic series is conditionally convergent. So our interval of convergence is the set -3 to 3. And if I had remembered how to do roots properly, the root test would have been a little easier. All right. One last thing before we finish. We're done with examples. Power series are differentiable and continuous on their interval of convergence. the radius of convergence of the series obtained by differentiating or integrating our power series is the same. So if we differentiate or integrate a power series, our radius of convergence is the same as the original convergence. The interval of convergence may be different. The endpoints after we differentiate or integrate may converge or diverge differently than the original series. So when we differentiate or integrate a power series, our radius of convergence is the same. We have to reconsider the endpoints. It may not converge at the endpoints. And we'll talk a little bit more about differentiation and integration of power series tomorrow. And we'll tie our power series to our Taylor polynomials. And it's really in the differentiation integration where power series become very useful for stuff in various different applications when we can find a power series representation of a function. All right, questions? Try the homework. Uh-oh.
Yep. Yeah, you can just dunk it with some more. So we don't have to maybe draw our lines. I don't want to risk it.
Do this one while you're sitting under a ladder. After you break a mirror. Yeah, while petting a black cat. It's close to Halloween, too. What's that?
You supply all those things that I will do it.
Mr. Beamer.
Yes.